March 7, 1923. Chicago's sprawling rail yards. The maintenance report stacked on General Motors research director Charles Kettering's desk would have made European locomotive builders nod in resigned agreement. American railroad executives attempted to solve the most persistent problem in yard operations using technology that violated 70 years of proven steam locomotive principles. Through the coal smoke and thundering steam of the busiest switching yard in North America, a small experimental diesel locomotive sat waiting for its first real test. No boiler, no complex valve gear, no traditional railroad design philosophy whatsoever. Yet, it was about to handle switching duties that had burned out 3 steam switchers in the past 18 months. In railroad yards from Philadelphia to Kansas and the city, conventional steam switchers required constant water stops and coal refills during 12-hour shifts. Each locomotive needed a dedicated fireman to maintain steam pressure, creating labor costs that consumed 40% of switching operations budgets. Most steam switchers lasted 8 to 12 years before boiler wear and frame stress forced expensive rebuilds or scrapping. The constant starting and stopping of yard work destroyed mechanical components designed for mainline running, not the brutal punishment of moving one car at a time hundreds of times daily. The Americans were attempting something railroad engineers considered mechanically foolish: a diesel-electric powertrain that eliminated boilers entirely, making electricity an intermediate step instead of burning coal directly for mechanical power. A compact design barely half the size of conventional switchers, but claiming equal pulling power through electrical torque multiplication. 3,000 miles from European locomotive works, the most decisive railroad revolution in industrial history was about to prove itself. Not through superior size, not through proven steam technology, but through one simple question that railroad engineers never thought to ask. What if yard locomotives did not need to be miniature versions of mainline engines? Charles Kettering stood in General Motors' experimental shops in Cleveland, staring at the problem that had consumed railroad operations departments for decades. At 57, he had revolutionized automotive ignition systems and electric starters, watching engineers solve problems through electrical innovation rather than mechanical complexity. The mathematics were brutally direct. When you operate a steam switcher in yard service, you must maintain boiler pressure constantly, even during idle periods between switching moves. The coal consumption continues whether the locomotive is working or waiting. The water must be replenished every few hours, regardless of actual work performed. The fireman's wages accumulate throughout the shift based on time, not productivity. Scattered across his workbench lay technical specifications from Baldwin Locomotive Works, American Locomotive Company, and Lima. Every design followed the same principle that had dominated railroad motive power for 70 years. Burn coal to boil water, use steam pressure to drive pistons, convert reciprocating motion to rotary wheel power. The inefficiency was staggering, but accepted as the inevitable cost of railroad operations. Beyond his workshop windows, the sounds of American railroading revealed the scope of the crisis. Steam whistles marked shift changes at yards that operated on schedules dictated by coal and water availability rather than actual switching demand. The railway executives' resistance came from hard experience rather than stubborn tradition. Kettering had documented every objection in his leather-bound notebook, numbered arguments that reflected decades of railroad operational reality. The diesel engine itself remained fundamentally unproven for continuous duty operations. Winton Engine Company's marine diesels powered boats that operated intermittently with long maintenance periods between voyages. Railroad switching demanded 12 to 16 hours of continuous operation daily, starting and stopping hundreds of times without cooling down periods. No diesel manufacturer could guarantee engine survival under such punishment. The electrical generation and motor systems added complexity that steam switchers avoided entirely. Every additional component created another potential failure point in operations where downtime meant backed-up trains and delayed freight movements. Railroad mechanical departments trusted steam technology because 70 years of development had refined it to known failure modes with established repair procedures. At the Chicago and Northwestern Railway headquarters, Superintendent James Walsh reviewed the diesel proposal with his master mechanic standing beside maintenance reports that told their own story. His yards operated 42 steam switchers that collectively required 16,000 hours of maintenance monthly. Each switcher needed daily inspections, weekly boiler washes, monthly valve adjustments, and quarterly frame examinations. The maintenance department employed 124 workers exclusively for switcher service. Walsh's calculations revealed costs that General Motors sales engineers preferred not to discuss openly. A new Baldwin steam switcher cost $28,000, delivered and track-ready. The experimental diesel-electric carried a price tag of $42,000 with no performance guarantees. The cost difference would purchase 3 years of coal and water for conventional operations. The weight specifications troubled railroad engineers who understood track and bridge loading limits. Steam switchers distributed their weight across driving wheels connected directly to cylinders and rods. The diesel-electric concentrated generator and electrical equipment weight in the center of the locomotive frame, creating point loads that existing rail infrastructure might not safely support. Railroad mechanical departments maintained extensive spare parts inventories for steam locomotives. Pistons, valves, tubes, and driving wheel sets were standardized across manufacturers with established supply chains and competitive pricing. Diesel-electric components required specialized suppliers with no competition and no established reliability records. A failed electrical generator could shut down operations for weeks while replacement parts were manufactured and shipped. The operational experience from European railroads offered no comfort. German diesel locomotives remained experimental curiosities used on branch lines with light traffic. British railways had tested diesel rail cars but rejected them for mainline service due to reliability concerns. French railroads continued ordering new steam locomotives while maintaining their position as Europe's most modern rail system. At Baldwin Locomotive Works in Philadelphia, engineers examined General Motors' diesel-electric specifications with professional skepticism. Their pattern books contain 70 years of steam locomotive development, representing thousands of design refinements based on actual service experience. The diesel proposal looked like amateur engineering from automotive manufacturers who understood cars, but not railroads. The fundamental question facing American railroading was whether unproven diesel-electric technology justified abandoning steam power that worked reliably despite its inefficiencies. Railroad executives were not opposed to innovation, but they were deeply opposed to innovations that could paralyze freight operations through mechanical failures that their shops could not repair. Through the winter of 1923 into 1924, General Motors' Electromotive Corporation took the engineering approach that would define diesel locomotive success for generations. Rather than attempting to match steam switcher complexity with diesel equivalents, they designed for brutal simplicity that eliminated components rather than optimized them. The first production switcher that emerged from the partnership between General Motors and Ingersoll Rand reflected this philosophy in every specification. The Winton 201A diesel engine delivered 300 horsepower, deliberately conservative compared to steam switchers rated at 450 horsepower. But the electrical transmission multiplied that power through torque characteristics that steam could never match. Harold Hamilton, the lead engineer, had spent months studying yard operations with stopwatches and notebooks. His observations revealed what steam locomotive designers had never optimized for. Switchers spent 60% of their time at speeds below 5 miles per hour, moving single cars and shortcuts through congested yards. The remaining 40% involved repositioning moves at speeds rarely exceeding 15 miles per hour. Electric motors delivered maximum torque at zero speed, exactly when switchers needed greatest pulling power. Steam locomotives delivered maximum power at higher speeds, requiring skilled engineers to manage wheel slip during starting efforts. The diesel-electric could start a 40-car cut from a standing position without drama, while steam switchers required careful throttle management to avoid spinning drivers. The mechanical simplicity became apparent when Hamilton walked railroad maintenance chiefs through the first production unit. No boiler meant no boiler inspections, no tube replacements, no firebox repairs, no reciprocating rods meant no bearing adjustments, no crosshead maintenance, no valve timing calibrations. No complex valve gear meant no piston ring replacements, no steam chest repairs, no cylinder boring operations. The entire power plant could be accessed through side panels that required ordinary hand tools rather than overhead cranes and specialized equipment. The electrical generator sat bolted directly to the diesel engine with 4 mounting bolts rather than being integrated into the frame structure. The traction motors mounted to the trucks with simple mechanical connections that took hours to remove instead of days. But Hamilton's most radical simplification came in the operator's cab, where steam switcher controls included throttle, reverse lever, independent brake, automatic brake, boiler water level, steam pressure gauge, lubricator controls, and blower valve. The diesel electric had a throttle with 8 positions, a reverse lever, and 2 brake valves. An operator could be trained in days rather than months. The first demonstration units entered service at the Baltimore and Ohio Railroad's Waverly Yard in Baltimore during April 1924. The railroad assigned the diesel electric to the most demanding switching district, a deliberate test that would expose any weaknesses quickly. The district handled classification yard work that required moving 300 to 400 cars daily through a series of tracks that demanded constant acceleration and deceleration. The diesel switcher worked alongside steam switchers performing identical duties, providing direct performance comparison that would determine whether General Motors' gamble on simplicity could overcome railroad skepticism about unproven technology. The question was not whether the diesel could match steam performance, but whether it could survive the punishment that destroyed steam switchers within a decade. The Baltimore and Ohio's Waverly Yard provided the crucible that would validate or destroy diesel-electric switching technology. Through spring and summer of 1924, the experimental switcher accumulated operating hours that revealed performance characteristics no one had predicted. The first month's statistics shocked both railroad officials and General Motors engineers. The diesel-electric operated an average of 14 hours daily compared to 9 hours for steam switchers that required frequent servicing. No boiler washes meant no 3-hour maintenance stops during shifts. No coal and water stops meant continuous operation limited only by crew changes and track availability. Master mechanic Robert Crawford documented maintenance requirements that challenged 70 years of steam locomotive experience. The diesel switcher required lubrication checks every 7 days, equivalent to what steam switchers needed twice daily. Electrical system inspections occurred monthly versus the weekly bearing and valve examinations that steam operations demanded. The first major maintenance intervention came after 93 days of service when the engine oil was changed, a procedure requiring 4 hours compared to the 8-hour quarterly boiler inspections that steam switchers underwent. But the reliability revelation came from what didn't break. Steam switchers typically experienced mechanical failures every 18 to 22 operating days. Blown cylinder packing, broken valve stems, leaking tubes, cracked frames, the failure modes were familiar and predictable. The diesel-electric accumulated 6 months of service without a single mechanical failure that stopped operations. Crawford's detailed reports revealed operational advantages that transcended simple reliability statistics. The diesel-electric started instantly without the 30-minute warming period that steam switchers required. Operators could shut down the engine during extended idle periods, then restart within seconds when switching assignments resumed. Fuel consumption tracked actual work performed rather than time elapsed, reducing operating costs by amounts that justified the higher purchase price. The performance data attracted attention from railroad mechanical departments nationwide. By October 1924, representatives from Pennsylvania Railroad, New York Central, Santa Fe, and Union Pacific had visited Baltimore to observe the diesel switcher in actual service. What they witnessed contradicted their fundamental assumptions about locomotive reliability. The Pennsylvania Railroad placed an order for 2 diesel switchers in November, designating them for the Enola Yard near Harrisburg, where brutal switching assignments destroyed steam locomotives. New York Central ordered 1 unit for testing at their DeWitt classification yard in Syracuse. Santa Fe requisitioned 3 units for yard service in Argentine, Kansas, where coal smoke restrictions made steam operations increasingly problematic. General Motors Electromotive Corporation responded by expanding production capacity in Cleveland, hiring engineers from steam locomotive manufacturers who brought traditional railroad knowledge to diesel-electric development. The switcher designation became SW-1, acknowledging that this was merely the first step in a diesel revolution that would eventually eliminate steam power entirely. Through 1925 and 1926, the SW-1 population grew to 47 units operating in yards from Boston to Los Angeles. Each installation accumulated reliability data that supported what Baltimore and Ohio had discovered. The diesel-electric switcher was not marginally better than steam technology. It was fundamentally superior in every metric that mattered for yard operations. Fuel costs, maintenance requirements, availability, and operational flexibility all favored the diesel design by margins that made cost comparisons irrelevant. The question facing American railroading shifted from whether diesel-electric technology worked to how quickly it could replace steam switchers that suddenly appeared obsolete. The true test of the SW-series switchers came not from carefully monitored demonstration runs, but from the relentless brutality of actual railroad yard operations that ground down equipment without mercy. Through the late 1920s into the 1930s, these compact diesels faced punishment that would reveal any weakness in their deceptively simple design. At the Pennsylvania Railroad's Enola Yard, the largest classification facility east of the Mississippi River, SW-1, number 2314, entered service in December 1925 on the hump lead assignment. This position required the locomotive to push cuts of cars over the classification hump 12 to 18 hours daily, starting and stopping hundreds of times per shift. The mechanical stress from constant acceleration and deceleration had historically destroyed steam switcher frames within 5 years. Mechanical foreman Edward Mitchell documented performance that defied his 40 years of steam locomotive experience. The SW-1 accumulated 1,000 operating hours in its first 73 days, equivalent to what steam switchers required 4 months to achieve when accounting for servicing downtime. The traction motors delivered consistent starting effort regardless of temperature, eliminating the wheel slip problems that plagued steam switchers in cold weather. The electrical transmission proved its value during the brutal summer heat that turned classification yards into furnaces. Steam switchers suffered declining performance as ambient temperatures increased boiler strain and reduced steam pressure. The diesel-electric maintained consistent power output because the engine ran at controlled temperatures with radiator cooling that adapted automatically to thermal conditions. Mitchell's maintenance logs revealed the remarkable durability of components that railroad engineers had predicted would fail quickly. The Winton diesel engine reached 5,000 operating hours with only routine oil changes and filter replacements. The General Electric generators operated without bearing replacements through 8,000 hours of continuous service. The traction motors accumulated 10,000 hours before requiring commutator maintenance that took 6 hours to complete. By 1930, Pennsylvania Railroad operated 23 SW-series switchers across their system, with reliability statistics that made steam switcher performance look primitive. The diesel fleet averaged 93% availability compared to 68% for comparable steam switchers. Maintenance costs measured 42% lower than steam operations when normalized for equivalent work performed. Most remarkably, none of the diesel switchers had required major mechanical repairs beyond scheduled component replacements. The Great Depression paradoxically accelerated diesel switcher adoption as railroads desperately sought operational cost reductions. Freight. Traffic declined by 40% between 1929 and 1933, forcing railroad management to eliminate every unnecessary expense. Steam switchers required similar maintenance whether they worked 8 hours or 12 hours daily due to boiler servicing requirements. Diesel switchers could be shut down during slack periods, consuming zero fuel and requiring minimal attention until traffic resumed. Santa Fe Railway conducted a comprehensive cost analysis in 1932, comparing their Argentine yard operations using mixed steam and diesel switchers. The data revealed that diesel operating costs per car switched measured 38% lower than steam, with the difference primarily from fuel savings and reduced maintenance labor. The railroad immediately ordered 12 additional SW units and began planning steam switcher retirements. The switchers were not just surviving railroad service. They were thriving in conditions that destroyed steam locomotives, proving that simplicity combined with robust electrical engineering could withstand punishment that mechanical complexity could not handle. Through the 1930s and into the 1940s, the SW-series switchers compiled operational records that transformed them from experimental curiosities into railroad industry legends. The statistics emerging from yards nationwide documented reliability levels that steam locomotive technology could never approach. At Chicago and Northwestern's Proviso Yard, SW1 number 1012 became the subject of intensive study by the railroad's mechanical department. The locomotive entered service in March 1927, assigned to the westbound classification district, the yard's busiest switching territory. Superintendent Walsh, initially skeptical of diesel technology, ordered detailed documentation of every maintenance intervention and operational hour. By January 1940, the locomotive had accumulated 78,000 operating hours over 13 years of continuous service. The maintenance record revealed numbers that seemed impossible by steam locomotive standards. The original Winton diesel engine remained in service with only normal wear component replacements. The electrical generator had been rewound once after 53,000 hours, a scheduled maintenance procedure rather than a failure repair. The traction motors operated on their original armatures with only bearing and brush replacements. The financial analysis shocked railroad executives who had built careers around steam locomotive economics. The SW1's total maintenance cost over 13 years measured $63,000, including routine servicing and the generator rewind. A comparable steam switcher operating equivalent hours would have required 2 complete boiler replacements, 3 frame rebuilds, and countless valve, piston, and bearing repairs totaling $147,000 at 1940 prices. But the remarkable records came from switchers that exceeded even these impressive statistics. Southern Pacific's Oakland Yard switcher, number 1043, compiled 91,000 operating hours by 1945, with only one major repair when a traction motor failed after 73,000 hours due to a lubrication system malfunction. Baltimore and Ohio's number 897 operated 18 years without a single unscheduled out-of-service event, accumulating 86,000 hours in classification yard service. The United States railroad industry documented the transformation through comprehensive statistics compiled by the Association of American Railroads. By 1945, 963 SW-series switchers operated nationwide with a fleet average availability of 91%. Steam switchers in comparable service achieved 64% availability. The diesel fleet's mean time between failures measured 2,300 operating hours. Steam switchers averaged 320 hours between mechanical incidents requiring shop attention. The wartime traffic surge of 1942 through 1945 provided the ultimate reliability test. Railroads operated at maximum capacity, moving military freight with minimal maintenance resources as skilled workers joined military service. SW-series switchers maintained performance levels, while steam switchers struggled with deferred maintenance and depleted spare parts inventories. Several diesel switchers compiled 48 consecutive months of service without entering shop facilities for anything beyond routine inspections. Master mechanics who had spent careers maintaining steam locomotives found themselves managing diesel switcher fleets that required skeleton maintenance crews. The transformation freed railroad resources for mainline operations, while yard productivity increased through equipment that worked reliably instead of breaking down predictably. The SW-series had proven that diesel-electric technology was not the future of railroad switching. It was the present, and steam power was obsolete. The final validation of the SW-series switchers came through the decades that followed their introduction, as the simple yard engines compiled service records that made them the longest-lived locomotives in American railroad history. Through the 1950s, 60s, and beyond, these diesel switchers continued working long after newer, more powerful locomotives had been scrapped and forgotten. By 1960, the oldest SW1 units had accumulated 36 years of continuous service. Railroad mechanical departments discovered that proper maintenance could extend diesel switcher life almost indefinitely because the simple design eliminated the structural failures that eventually destroyed steam locomotives. Boilers corroded and weakened over time, regardless of maintenance quality. Diesel engines could be rebuilt repeatedly using the same basic structure. The Pennsylvania Railroad's number 2314, which had entered service at Enola Yard in 1925, was still switching cars in 1973. 48 years of service, 216,000 operating hours, 3 engine rebuilds, 4 generator replacements, and 6 traction motor overhauls. The locomotive's maintenance cost per operating hour measured less than comparable steam switchers had achieved in their brief operational lives. Across American railroads, SW-series switchers became permanent yard fixtures that outlived their corporate owners. Units purchased by Baltimore and Ohio continued working after the railroad merged into CSX in 1980. Chicago and Northwestern switchers migrated to Union Pacific when that railroad absorbed their original owner. The locomotives changed paint schemes and road numbers but kept performing the unglamorous work that had defined their entire existence. The remarkable longevity resulted from the design philosophy that Harold Hamilton had established in 1923. Simple components that could be maintained with basic tools, robust construction that tolerated abuse rather than requiring careful operation, electrical systems that failed gradually with warning rather than catastrophically without notice. The SW-series represented engineering for reliability rather than performance, prioritizing availability over capability. Railroad historians documented the cultural impact of locomotives that defined diesel-electric reliability. Yard crews developed fierce loyalty to specific switchers that had served their operations for decades. Mechanical departments maintained SW units with pride, knowing that proper care would keep the locomotives working essentially forever. The switchers became institutional memory machines, surviving multiple generations of railroad managers and outlasting corporate restructurings that eliminated their original owners. The final SW-series switchers remained in regular service into the 21st century, with several units achieving 80-plus years of operation. These locomotives had worked through the Great Depression, World War II, the Jet Age, the Computer Revolution, and the Internet era. They started service pulling wooden boxcars and ended their careers moving double-stack container trains. Through all of it, they kept running with the mechanical consistency that made them railroad industry legends. The story of the SW-series switchers demonstrates that revolutionary technology does not require complexity or sophistication. Sometimes the most reliable machine is the one designed to be simple, built to be strong, and engineered to last. In American railroad history, no locomotive better exemplified these principles than the modest yard switcher that General Motors introduced in 1923 and railroads operated for more than 80 years afterward without finding anything better.